So we encounter now our next convergence test, which is called the alternating series test, or the AST, and it's sometimes called the Leibniz test. So what this is a way of testing whether an alternating series converges. So let's let AN be a positive decreasing sequence. When I say decreasing, what I mean is that well, first of all, when I say it's positive, what I mean is that all the terms in the sequence are in fact greater than zero. When I say it's decreasing, I mean that in the algebraic sense, where I mean that for every term, an plus 1 is going to be less than its previous term. So the sequence is, if I were to map it out like this, it's always getting smaller. That's what I mean by it's decreasing. So once we have a positive decreasing sequence, if the limit as n approaches infinity of an, in other words, the limit of the sequence, not the series, but the sequence is 0, then we can say that the alternating series that you form by taking that sequence and making it alternate, those series converge. And the reason I've said both of these converge is it doesn't matter whether I make the first term negative, as in this case, or if I make the first term positive, as in this case. If it alternates and this limit is true and we have a positive decreasing sequence, then the series converges. So here's an example of what we can do with the alternating series test. Let's determine whether the series -1 to the n over n converges absolutely, converges conditionally, or diverges. So there are a couple of different orders in which you can test this. One thing that's often kind of useful is to see if the series converges absolutely, because if it converges absolutely, you don't even have to test whether the series itself converges, because we know by the absolute convergence test that if a series converges absolutely, then it also converges. So let's first see if the series converges absolutely. Let's test the series absolute value of -1 to the n over n. Well, what this does is it just basically takes out that -1 to the n term, because what that's going to do is it's going to turn half the terms negative, but the absolute value of a negative term is positive. So this is just equal to this series. And of course, we know that this diverges because it's a p-series with p equal to 1, which is less than or equal to 1. Or, do you recall, there's another name for this particular series, which is, we could say it's the harmonic series. That's the special name for the p-series with p equals 1. So, all right, so we can certainly say that the series does not converge absolutely. But we're not quite done yet, because it's possible that the series converges conditionally, even if it doesn't converge absolutely. So what we need to do is find out whether the series itself converges. So for that, we're going to observe that this is an alternating series. Now, how do I know it's an alternating series? Move this up a little bit. How do I know this is an alternating series? Well, I mean, I know I can determine it's an alternating series just by looking at it, because clearly it's going to flip around positive and negative. But we need to verify that it does meet the conditions of the alternating series test, which were that the series has to be that the underlying series, once you take away this -1 to the n term, has to be positive and decreasing. So let's define an to equal 1 over n. So then we can see that the series is in fact the sum from n equals 1 to infinity of -1 to the n an. So let's verify, is an positive and decreasing? Well, it's certainly positive, because 1 over n is greater than 0 for all n greater than or equal to 1. Since we're starting this series at 1, that's the relevant value of n. So we can certainly see that it's positive. Now, is it decreasing? Well, it's not difficult to see that 1 over n plus 1 is going to be less than 1 over n for all n greater than or equal to 1, because we're just making the denominator bigger and bigger and bigger, so we're making the fraction smaller. So since each successive term is less than the previous one, the series is decreasing. In other words, if you were to map it out, it would look sort of like this. So you can see that the positive term is getting smaller and smaller. So we do have that an is positive and decreasing. Therefore, we calculate the limit as n approaches infinity of an, which is the limit as n approaches infinity of 1 over n, which we can easily see is 0. So if we have a positive decreasing sequence an, what does the alternating series test says? say it says that by the alternating series test, AST, the sum from n equals 1 to infinity of negative 1 to the n, an, converges. And this is, of course, we know that this is just equal to the original series that we were given. That's negative 1 to the n over n. So we've shown now by the alternating series test that this series converges. So let's sum it all up. We've shown that the sum from n equals 1 to infinity of negative 1 to the n over n, the absolute value bars around it, diverges, but the sum from n equals 1 to infinity of negative 1 to the n over n converges. So we can conclude that the sum from n equals 1 to infinity of negative 1 to the n over n converges conditionally. And that's the answer. Let's see if I can fit this whole thing on the page, just barely. There we go.